me through this. Thank you. I will begin with a word of prayer. So, Dear Father, we thank you for this day. I thank you for these students. Just ask you to bless this class and just give these students energy and time and motivation to work on this course this semester. Lord, in your name I pray. Amen. All right, so this is, of course, linear algebra. I have posted the course planner and syllabus and all that stuff, so I'm just going to get right into the math. So let's talk about numbers, right? And by that I mean, well, we have notation for various things, right? Let's just put some of them down here. So what's this typically notation for? Z is what? Integers, right? So you could say 0, plus or minus 1, plus or minus 2, and so forth, right? How about natural numbers? What are those? 1, 2, 3. Some people throw in 0. Those people are wrong. I'm just kidding. Those people are in other countries. That would be me some semesters, but not this semester. Natural numbers. Of course, we also have Q, which is what? Rational numbers like P over Q, such that what? P and Q are integers, and what else? All right. So these are the so-called rational numbers. So wait a minute, doesn't that mean that pi is rational, right? It's the ratio of the what? Circumference to the diameter. Doesn't that make pi a rational number? This is a, yeah. I mean, there's an obvious. One of them won't be. Right. That means that we cannot construct a circle that has both integer circumference and diameter. That is what's implied by proving that pi is irrational. So an irrational number is everything except for the, it's everything beyond that in the real numbers, right? So I'll just give you another notation for it, right? At the moment, I haven't really told you how to construct any of these things, right? But you know what they are, and we're going to behave as if you know what they are. In particular, we know how to add things, multiply things, divide when it's appropriate, right? Okay. What else can we talk about? Oh, complex numbers, right? What do complex numbers look like? A plus bi, such that a and b are real numbers. And what? I squared is minus 1, right? Past that, we multiply, we assume associativity and distributivity as usual. And so you've had some experience with complex number arithmetic before. You'll get more in this course from time to time. All right, so I should talk to you a little bit about terminology. So if R is a set with a binary operation of addition, so it goes from R cross R to R again, and multiplication, which goes from R cross R, oh, wrong R. There's no double bar here. This is just R as an R, not as in the real numbers. So here, we take the pair A comma B and we map it to A plus B. There's a single assignment, A, B maps to AB. So this is multiplication. This is addition. I'm saying that these are functions in the sense that if you give me a pair of numbers, there's a unique sum, right? And there's a unique product, right? I'm saying suppose R has this structure. It's got something called addition. It's got something called multiplication, right? If you have addition and multiplication like that, and the addition and multiplication satisfy all the familiar rules that you know, what are those familiar rules? What are the rules that addition and multiplication should satisfy? Yeah, sure. Let's say associativity. So how about this? A plus B plus C makes sense, right? What do I mean by that? let me make that a little bit less. What's associativity of addition is what? It's this is equal to that, right? What else do we know about addition? How about it's commutative, right? A plus B is equal to B plus A, the commutative property of addition. What else do we know about addition? There's something called 0, right? Yeah, there's an additive identity. So for all x in the ring, we have that x plus 0 is equal to x, which of course is also equal to 0 plus x. I mean, it's commutative. We're assuming that the ring is commutative. Oh, I said ring. What's a ring? That's what I'm describing right now. A set together with two operations, addition and multiplication, is called a ring. All right? So a ring is a set where you have an addition and a multiplication, and they behave like you're used to. Right? So we have as addition, which is associative, commutative. There's an additive identity. You have negatives for everything, right? So there exists, for each x in R, there exists minus x in R such that what? X plus minus x is equal to 0. So for every number, there's an additive inverse for each number, all right? And then what about multiplication? What about the multiplication? What are the rules for multiplication? It's commutative. Well, let's say it's associative. ABC is equal to ABC. So that's going to almost always be the case for things we're interested in. AB equals to BA implies that R is commutative ring. So there are rings which are not commutative, all right? But for the most part, we're going to be interested in commutative rings, at least as we think of them as numbers, all right? All of these are commutative rings, except for one. Which one of these is not a commutative ring? So can you tell me which one of these is not a commutative ring? Integers, natural numbers, rational numbers, reals, complex numbers. Which one of these is not a commutative ring? And why? What's that? I heard it. Rational. Oh, no. I'm going to take that rational and turn it into a natural, because that's what I heard. I heard natural. I'll hear what I want to hear. So why are natural numbers not a commutative ring? They're not a ring at all, that's true, yeah. That's true, all of these are commutative, fair enough, good point. But the natural numbers are not a ring because they don't have 0, right? And minus 1, minus 2, minus 3, they're missing, right? There's no additive inverse for the natural numbers, it's not a ring, okay?
So a ring is what exactly?
A ring is a set which has an addition and a multiplication which behave as usual. The addition is commutative, associative, there's an additive identity, there's an additive inverse for each element. The multiplication is associative, possibly commutative, and we assume that there's an identity, a multiplicative identity, which we call 1. All right. What other properties are there for multiplication? Then there's intertwining relations between the multiplication and the addition. What are those relations? Those are what we call distributive properties, right? So the distributive properties what are those? So like A times B plus C is what? AB plus AC, right? And that's sometimes called right distribution, and there's left distribution as well. Of course, in the commutative case, these are equivalent, right? If you've got one, you got the other. But these are this distributive property. And then once you have these, there's a bunch of other things you can prove. Like 0 times anything is what? Is 0, right? And minus 1 times a ring element is what? It's what? It's the it's the negative of that thing, which is to say minus 1 times something is the additive inverse of that something. That you can prove from these more basic axioms. All right. Now, this is not the focus of this course, right? I'm just introducing some terminology so that we know that you know what I mean when I say commutative ring. I'm just talking about a set with an addition and a multiplication. And things that we can prove about commutative rings, this is all the information we need. Just that we have these properties of associative addition, multiplication, the distributive properties, the things that are on the board, right? So I could start this course by talking about matrices with real numbers or complex numbers, right? But instead, I start the course by talking about matrices with elements from a ring because the proofs are the same and it's a good exercise in a simple kind of abstraction. See, because if I can prove a theorem about a commutative ring, I've proved that theorem for real numbers, for rational numbers, for integers, and for everything down the list, and for things that maybe you don't know about yet, right? Let me show you a commutative, so a little bit more here. Another example, which is probably less familiar, Z6, all right? So this is, I'll use bars, 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, all right? So Z, the integers modulo 6. These are not actually integers, they're actually sets of integers which we add in a specific way. Let me show you how it works. So like 2 plus 3, by definition, is 2 plus 3 bar, which is just 5 bar, all right? And on the other hand, if I was to say 3 bar plus 3 bar, what would I get? I would get, I would get 3 plus 3, which is 6 with a bar over it. And by definition, that's 0 in this interesting new set. So, I mean, here's the definition. K bar is equal to, if you like, it's the set of k plus n times j such that j is an integer. It's actually a set. It's a set of integers. But we can add those sets by just adding their representatives and then reducing mod n. Now, again, that's not the focus of this course. I'm just going to show you enough so that we can do some basic calculations, all right? If you're taking number theory right now, you're probably going to do a lot more with this, all right? Eventually. Not right off, but here's another one. If we were to do, say, 5 bar plus 2 bar, that would be 7 bar, right? So, but that's actually equal to 1 bar. So the larger point here is x bar is equal to y bar if and only if y minus x is equal to n times j for some j in the integers. In other words, two equivalence classes are equal if they differ by a multiple of n. So what that means pragmatically is we can like eat copies of n. So this 7 is really 6 plus 1, right? And so we can just eat the 6 is what it ends up meaning. Another thing I could say is that x bar is equal to, you know, like y plus any multiple I can add any multiple of n to that and get the same set of natural numbers, same residue class as it's called. All right. Let's see here. Let's just do a multiplication table right quick. 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. Why didn't I should have done this for something smaller. Goodness gracious, why didn't I do this for 4? Oh well, it's too late. I'm too far in. Sorry. All right. Well, some of this is very easy. I'm going to make a multiplication table. All right, make a multiplication table here. So what 0 times anything is? Right, and 0 bar behaves as the 0, by the way, all right? And 1 bar behaves as the 1. So there's nothing too surprising there. So we've got 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And 1 times anything is that anything. So I got 1, I got 2. Oh, I'm sorry. I'll get it together eventually here. I've got 1, 2, 3, 4, 5, 2, 3, 4, 5. All of these should have bars on them. Eventually, this starts feeling stupid, so you stop writing the bars, all right? But then, if you stop writing the bars, you need to write something at the start which says working modulo n or something so that your reader knows what you're doing, right? If you just write stuff like 1 equals to 7, people might be kind of like, but that's true, mod 6, right? That's true. Although usually in number theory, you will also do this. So you talk about 1 being congruent to 7, but I say that 1 is equal to 7 mod 6 in Z6, okay? All right, anyway. So these are the kind of boring ones. Let's continue. What's 2 times 2? 4. So we got 4 bar. 2 times 3 is 6 bar, which is 0, right? 2 times 4 is 8, which is 2. 2 times 5 is 10, which is 4. And it's symmetric, like that pattern, like that. Let's see here. 3 times 3 is 9, which is 3. 3 times 4 is 12, which is 0. 3 times 5 is 15, which is 3. 4 times 4 is 16. I regret this, which is 1. 20 is 2. And 5 times 5 is 25, which is 1. All right. So this is really the only other example I have in mind for you guys. And here, the ring, I mean, I'm introducing the concept of a ring as an abstract idea, partly just to plant that seed for Math 421. All right? Like, we will study rings, not me, probably Dr. Sprano and you guys will study rings either in 421 or 422 in the abstract, in much more abstraction and in detail. For us, I'm just using it as a linguistic device. Really, the only examples I have in mind are what I have on the board already and Zn. Well, not just 6, but with an n. And that's plenty. That's plenty for us. But so in some sense, this abstraction is not entirely needed, but I think it's a good exercise just to get used to language. Now, the important thing here, though, about this example is it's got some really weird behavior, right? Did you notice this? 2 bar times 3 bar is equal to what? 0 bar. Is this 0? No. Is that 0? No. So we have the product of two non-zero things is 0. That's weird, right? That's not familiar to our experience. Let's see here. What else? On the other hand, we have some kind of neat stuff, like 4 times 4 is what? Is 16, but 16 is, well, it's 1, right? So this means that 4 bar inverse is equal to 4 bar. In other words, 4 is its own multiplicative inverse. In some sense, slight abuse of notation, but you could say that 4 is equal to 1/4 in Z mod 6. Weird, right? It's also true for 5. See, 5 times 5 is what? It's 1, yeah. So the multiplicative inverse of 5 is also 5. This is not familiar, right? Yeah.
4 bar times 4 bar should be 4 bar.
Oh, did I do that? Oh, man. Son of a gun. 4 bar times 4 bar. Is that right? 4 bar times 4. Oh, yeah. Thank you. Curses. I wanted it to be 1. Oh, reality got in the way of my wishes. Oh, well. Fine. I mean, just as I intended for your learning. But 5 times 5 is 25, right? 25 mod 6 is, this is right? Yeah, okay. I should know this anyway. What are the numbers that are relatively prime? Relatively prime to 6 or what? What numbers are relatively prime to 6? 1? 2 is not, 3 is not, 4 is not, and 5. There are only two numbers which are relatively prime to 6, namely 1 and 5, and those are exactly the numbers which have multiplicative inverses in Z mod 6. You should say, thank you, I just did 3 weeks of your number theory course. Okay, no, I mean, that's going to be a big part of it. But I'm joking, mostly. Okay, so one last bit of terminology, then I will actually start talking about matrices. In a commutative ring, we have things which are zero divisors, right? So like these are zero divisors. On the other hand, this makes 5 bar a unit. A unit in a commutative ring is an element which has a multiplicative inverse. All right? So, definition, a commutative ring in which every non-zero element is a unit is called a field. All right? So the examples I started with, some of those are fields and some of those are not. Which of my 5 basic examples are field? We already ruled out the natural numbers. They're not even a ring. Rationals are a field. That is true. What else? The reals are in fact a field. A complete ordered field, whatever that means. The complex numbers, again, a field because the reciprocal of a complex number we multiply by the conjugate over the conjugate. Remember, there's a nice trick for finding the multiplicative inverse of a complex number. So yes, the complex numbers form a field. What about integers, though? Are there zero divisors in the integers? Well, no. I mean, like, I can't have a product of two integers 0 unless what? One of the integers has to be 0, right? This we know. But, so no zero divisors, right? Non-zero zero divisors, at least. Some people would say 0 is a zero divisor. That's kind of a point of contention on depending on what you look at. Usually when I say zero divisor, I'm talking about a non-zero zero divisor. I mean, 0 is always 0 times 0, right? So whatever. But what's the inverse of like 2 in the integers? It's a half. But a half is not in the integers, right? So no, the integers are not a field. This is important because as we go on in here, we're going to learn how to manipulate matrices with entries from a field. If we have a field, that means we have multiplicative inverses and we can do basically division operations. On the other hand, if we were looking at a matrix that was just with say integer entries and we didn't have fractions to work with, then that would limit us. We wouldn't be able to do steps which are based on division. All right? So anyway, that's the backdrop. So I don't have too much on calculations over Zn in this course, but there is some, so I wanted to introduce it because I know Z mod a natural number is maybe a completely new thing for you, right? So I think it's important to at least try to demystify it. It's not hard, you just have to work with this idea that you can eat multiples of the copy of n, whatever that is, right? What would make Z mod what would be a field? If you believe what I said without proof that the set of numbers which are relatively prime to the modulus here is 6, are the units, right? So what would it take for Z sub n to be a field? Z1 is, I don't know what Z1 is. Let's say Zn n greater than 2. Let's talk about that. I think Z1 is probably the stupid ring where 1 and 0 are the same element, and we try not to talk about it. But there's always some wiseacre in the math major, right? Math major?
Somewhat.
Okay, somewhat. It's like, I don't like the way you answered that. Well, no. How about Z3? 1 and 2 are both going to have inverses, right? Like 1 times, well, 1 is 2 times 2 is 4, which is 1, right? So 2 inverse is 2 in Z mod 3. How about 5? If you just start thinking about it, if we have Z mod a prime, that's going to be a field, because any number is relatively prime to a prime. So the only thing that's 0 in there is 0. I mean, the only thing, the way to multiply to get 0. Anyway, there's no zeros divisors if n is prime is the... Sorry, I'm really taking the wind out of the sails of number theory right now. You forget everything I just told you. Be surprised when you find it in number theory. All right, I'm going to regret this. How much time have I spent on this? Oh, woe is me. Well, at least we gained a day this week, so it's not bad for me to blather on about rings too long. I know, I know. All right, so now chapter 2. So, matrix. So we now attempt to ask and answer the question, what is a matrix, right? So a matrix is a rectangular array of entries, really, all right? And for the most part, I want to think about a matrix with entries from a commutative ring, okay? And so just here's the terminology. If A is in R m by n, so let's agree that R denotes a ring, a commutative ring, right, going for the rest of this lecture. So if A is in R m by n, then A is an m by n matrix, all right? And what does that look like? Well, A looks like this. A11, A12, A1n, n as in nanu nanu, and then we have A21, A22, A2n, all right, again, n as in nanu nanu, not to be confused with m. So AM, m as in mommy, AM2, AMN. All right. You're like, that's not really a definition. Well, okay, fine. If you want, you could give a more, technical definition which defines this in terms of like maps into some horrible space so that you can distinguish elements in the matrix, but I don't think this really adds anything. The point is that there is a way of constructing rectangular arrays of numbers such that two such arrays are only equal if they match in every single entry. All right, so what's the entry here? What's the ijth entry? Here, aij is an element of R, and this is called the ijth entry of A, or let's say component. All right. Now I and j are both indices. What is I? Here I is the row index. All right, and j is the what? Column index, right? And what can we say about I and j? Well, I can tell you that 1 is less than or equal to I is less than or equal to m, because an m by n matrix has m rows. So the row index ranges from 1 to m. An m by n matrix has n columns. The column index ranges from 1 to n. All right? It's understood. If you have an equation, all right, which has an I and a j, and they're taken for an m by n matrix, and you say for all ij, what does that mean? That's a shorthand for saying for all 1 less than or equal to I less than or equal to m, and for all 1 less than or equal to j less than or equal to n. This is important because in certain discussions, it would get very old if every time we had to qualify for which I and j it holds for, if we actually had to write down these inequalities every time we make a step, right? It's nice to have an agreement that when we write for all ij, it's with the understanding that I and j ranges over their full context. So an example of this language would be, well, this isn't really a definition, but I don't know what this is. I can't prove it because I haven't gotten into the substructure, but it's part of whatever makes a matrix, let's say that much. A equals to B. It's either a definition or an observation, depending on where you start. So you can take it for what you want. But A is equal to B if and only if Aij is equal to Bij for all I and j. And what's the context I mean here? I really should tell you A and B. A and B in Rm by n. Right. So A is equal to B if and only if they match in every entry. Again, if I wanted to really make you guys bored, we could spend a whole class developing how you actually build m by n entries of things such that you can distinguish entries. Do you know how to do it for like a 2-component vector? You can build the 2-component vector from sets. Do you know how? I mean, you probably have accepted that AB is only equal to CD if only what, right? A equals C and B equals D, right? This is something you've been doing since, I don't know, middle school? What is that, though? Like, how do you... So some people would say that that's something like a set, I forget exactly, it's something like this. It's some kind of set of sets. You can formally build pairs such that you distinguish the first from the second element by nesting sets. Right? So it is possible to construct such things, but does that matter? No, so we don't talk about it. Oops. We don't talk about it. All right. If this is, we talk more in office hours if this is troubling to you, what I just said. Anyway, the point is 2 matrices are equal only if all their entries match. What other terminology should we introduce for matrices? How about rows and columns, right? So if you like, we can talk about column J of A. This will be equal to A1J, A2J, AMJ. Right? This is the jth column of A. I should tell you, we have a notation because writing columns in the middle of paragraphs of text is a real drag. So we have a sneaky notation, and we agree that this is equal to A1J, A2J, ANJ, all right? That's parentheses actually mean columns. That's our notation. It's a sneaky notation, but it's a notation. What's the ith row of J? Ith row of A, actually. Just to make a distinction, that we use square brackets. So that's AI1, AI2. Commas are optional. Sometimes I'll draw commas, sometimes I don't. It's just a question of, whether they're needed to separate things or not. Those are just window dressing, right? They're not really there in some sense. It's easy to see where different rows are in a given column, right? You don't have any trouble distinguishing between one number and the other. But when we write a row, sometimes it gets hard to see which entry is next, What's the question?
So hypothetically, there's a homework problem where there is brackets with commas. You can kind of just ignore those commas.
Right. I mean, they're optional, but sometimes they need to be there just so the reader can tell which number is, If I write v equals to 1, 2, 3, 4, what do I mean? I mean, that depends on the context, right? If this is an element of our 1 by 2, which would mean which would mean real row vectors that are two-component row vectors, then there's, I guess, 3 interpretations. You could go like this. You could go like this. Or you can go like that. You know, so for this reason, it's important to put commas, because otherwise you can't tell where one number starts and the next one's. Yeah. All right, anyway. My larger point here is that the jth column of A is actually where this is an element of what? And this is an element of what? Fill in the blank for me.
I just have a question.
Go for it.
Are those notations supposed to have an N instead of an N?
Yeah, the row.
Oh, yeah, yeah. You know, I had it right here, but then somehow I lost it going to that step right there. Sorry about that. Thank you. I very much appreciate that question. That is the appropriate time to ask that question, too. Do not harbor those things internally and come to me at the end of class. Right? You can ask now. I welcome your questions. So the column is actually what kind of matrix itself? It is a m by 1 matrix. Right? And the row is actually a what? Oh, did I do that? I think I did. I'm an idiot. Grief. Eventually I'll learn 1 by n. Yeah. So 1 row, n columns versus m rows, 1 column. So we have these 2 different ways of kind of slicing and dicing a matrix. We can either look at matrix as a bunch of columns glued together, right? Or we can look at a matrix as a bunch of rows glued together. We take both viewpoints, and they're both important. Is there a way to convert like a row to a column or vice versa? There is, yeah. This is called the transpose. All right, so definition, if A is in R m by n, then a transpose is an element of R n by m, where A transpose ij is equal to A ji for all ij. All right? So this is how we transpose a matrix. So here's an example. If A is equal to 1, 2, 3, 4, 5, 6, then A transpose is equal to 1, 2, 3, 4, 5, 6. Basically, you just take each row and make it into a column. If the matrix is square, it just corresponds to like flipping it over the diagonal. What's the diagonal? See what I mean? In the case that the matrix, what's it mean for the matrix to be square? Yeah, equal number of rows and columns is called a square matrix. A square matrix has what's called the diagonal. What's the diagonal of a square matrix? The diagonal of the square matrix are the like II, or well, yeah, it's the entries of the form II. It's like 1, 1, the 2, 2, the 3, 3. Collectively, those form the diagonal of a square matrix. So the transposition of a square matrix, you can kind of see it as just flipping things over the diagonal, right? The diagonals stay fixed, and the off diagonals just kind of turn over. That's the transpose. So, all right. So what can we do with matrices? We have arithmetic, right? Arithmetic for matrices. How would you add two matrices? So if, let's suppose that A and B are m by n matrices again, right? Then A plus B, ij, is by definition aij plus bij. So to add two matrices, we simply add them component-wise. All right. We can also talk about the scalar multiple, like a scalar multiple of a matrix, right? Many of you have had calculus 3. Show of hands, who has not had calculus 3? So we have 1, 2, 3. Ed? All right, very good. So that's okay. Don't worry. You will learn some things about calculus 3 this semester. They're harmless. So CAIJ, this is the so-called scalar multiple. So we're multiplying a matrix by a number. Here C is just a number. And very simple definition, this is just CAIJ, like that. It's actually pretty easy to prove that the m by n matrices form a ring. Well, that's not quite true. Because the multiplication, I don't know what multiplication of a rectangular matrix with another rectangular matrix means. I will soon show you how to multiply square matrices, though. So if we have square matrices, those actually form a ring, because there's a way of multiplying. And the addition and multiplication of matrices actually is associative, and it has those nice distributive properties. On the other hand, we will also soon learn that matrix multiplication is not commutative. So it's actually kind of the most important example of a non-commutative ring, a set of matrices over a ring. But anyway, there's addition, there's multiplication, and then once we have this, we can prove things. Like, let's prove the distributive property for matrix. Oh, curses. I guess I need the matrix multiplication before I can do distributive property, right? So how are we going to multiply matrices? If A is in R m by n and B is in R n by p, then AB in R m by p is defined by A, B, parentheses, ij, is equal to the sum k equals 1 to n of A, I, k, b, k, j. So there's how we multiply two matrices. We can only multiply them if the number of columns in the left factor matches the number of rows in the right factor. We have to have the n here matching up in order to multiply the matrices. If they don't match up, you can't multiply them. Let's see here. So let me talk more about this matrix multiplication. A, B, ij equals to the sum k equals 1 to n of A, I, k, b, k, j. Right? another way we could look at this, all right, would be that this is the sum, k equals 1 to n, of, let's see here, that is row I of A, right? That's row I of A. It's the what? It's the kth component of the row, the ith row, right? And what's bkj? Well, that's column j of B, right? And it's the what? It's the kth column, kth component of that jth column. So, you know, row I of A, let me write it out again for you. This is A, I1, A, I2, A, I, how many? N, right? And column J of B, B1, well, excuse me, B1J, B2J, BNJ, right? So this notation means the kth component of row I, right? IK. The kth component of column J of B. So that would be this BKJ. All right? So this thing we're looking at, multiplying the kth thing with the kth thing and then adding them up as k ranges from 1 to n, this is called a dot product. This would be familiar to those of you who have Calculus 3. If you haven't had Calculus 3, well, I'm sorry, but, you know, this is row I of A, dot product with column J of B. So this is the other way we can look at matrix multiplication. One of the other ways is we're taking dot products of the rows of the left factor with the columns of the right factor. Let me show you an example with numbers. So if I had like 1, 2, 3, 4 times, let's see here, oh, oops, 5, 6, 0, 0. So does this multiplication make sense? I think it will, because we've got 2 by 2 times 2 by 2. So just to identify what's going on here. Stupid watch. Show me my time. It shows me everything except for the time. Aye, aye, aye. So here's an M. This is N, N, and P in my previous definition. All right. So what we have is like 1, 2, dot product with 5, 0. And let's see here, 3, 4, dot product with 5, 0, 1, 2, dot product with 6, 0, and let's see here, it was 3, 4, dot product with 6, 0, I think. Now, the notation I just wrote on the board, that whatever, it's not. Anyway, the point is that this is 5 plus 0. That is 6. 6 plus 0. This is 15 plus 0. This is 18 plus 0. So what do we get? So 515 for the first column and 618 for the second column. Wait a minute, that seems... Yeah, that seems right. Now, if you have not multiplied matrices before, this will not teach you it, right? And I'm not going to teach you how to multiply matrices in here. That's not what this course is about. You were going to learn in homework, okay? We will move on shortly. And so like next time, we should probably start by proving properties of matrix. So here's an exercise for you. See if you can prove for yourself that this is equal to that, right? Can you prove that? How would you go about proving that, right? So you have to use the definitions which have been stated, which are what? Matrix multiplication, matrix addition, right? The way I would do it is to look at the ijth component of one side and show that it's equal to the ijth component of the other side using definition of matrix addition, multiplication, and then properties of commutative rings. Right? So I'll try to do some things like that next class, but anyway. Sorry we didn't get further. I will have to add a video to catch up at the end of this week, but we're not there yet.